Okay, at last, here we are in Lecture 12. So welcome back, everybody. I hope everybody had a good mid-quarter break after the midterm. And that was actually planned this way, to sort of try to have a midterm, and I knew there'd be a little bit of break. We'll get back to it. The next couple of weeks are going to be very busy for us, because we're going to have a lot of stuff to cover, and we're going to have a lot of homework. So I hope you prepare for it. Is everybody prepared for lots of homework? No? Okay, well, that was last weekend was your break. This weekend won't be your break, at least in this class. What we're going to be doing today is arithmetic coding and channel capacity. So arithmetic coding is sort of the last topic on compression that we're going to be talking about. It's a stream code, a stream compression algorithm. We're going to be talking about that. And then we're going to start talking about, today mostly conceptually, about the idea of channel coding and channel capacity, which, as we will see, is in some sense the dual of compression. So there's compression where we want the rate to be small, and there's communication where we want the rate to be big, and there are duals. And there will be a dual concept to the entropy called the channel capacity, which we will define and discuss. There's a couple of new readings for everybody to do. The first is to read Chapter 7 in our book. That's the book on channel capacity. The other is actually on stream codes. It's actually Chapter 6 in David Mackay's book, Information Theory and Learning Algorithms. It's actually available online for free. He's extraordinarily generous in that sense, even though it's a very good book and a lot of people use it. And you can buy it in the store, and I encourage everybody to go out and buy the book. But he is generous enough to, in fact, I think all of his books that he's written, he makes them available for free. He's made a deal with the publisher that you can go and just download them for free from his website. This is his website. This is not a illegal site masquerading as his website, by the way, if anyone was wondering. Homework 5 will be out tonight. For the rest of the quarter, homeworks are going to be due on Thursday nights rather than Tuesday nights. As I mentioned in the announcement, which I hope everybody got, I unfortunately was not able to finish the YouTube lecture by today. On the other hand, I think as a result, today's lecture will be pretty good because I fixed a number of typos in the slides that I didn't notice before. So hopefully we will have a completely typo-free lecture, but I don't know. Maybe that's too much to hope for. However, I'll probably, in fact, early this week, add another hour or so of YouTube lecture. We're actually not really behind because we actually got a bit ahead. We got a bit ahead for the first half of the quarter. And now we're sort of on track. So it's not absolutely essential to do YouTube lectures, but maybe I will, but at a somewhat relaxed pace. But anyway, homework will be due tonight and due next Thursday, and we'll have a homework due every Thursday up until the final exam, which will be on a Tuesday, the Tuesday after the last homework is due. Okay, so
Can I ask a quick question?
Yep.
I got an email that tomorrow's the day for registering for classes. Could you give like a quick advertisement for the second round?
Oh, yeah, well, I encourage everybody to register for Information Theory 2, if only so that you don't miss out on all of the fantastic jokes that I have planned for next quarter. Information theory is a big topic, and to only take 1/4 of information theory, I think, is a crime. So there's two motivations. Not taking it is a crime. Number two, you get lots of good jokes if you take it. But in reality, I mean, if you don't learn about rate distortion theory, for example, and Kolmogorov complexity, and network information theory, you'll really be missing out on some amazing material. And also, some of the stuff that we'll be talking about next quarter will really be at the forefront of information theory. Some very modern papers that we'll review and some other things that we'll look at, including some material from El Gamal's book, which is, he's written this fantastic book on network information theory. So it's more advanced on the other hand, but on the other hand, it's really interesting, and you'll get up to speed. I mean, by the end of next quarter, if you take it, you'll be, I think, able to read any paper at an information theory conference, and also just fundamentally understanding the idea of when you are allowing distortion, because in some sense most compression algorithms these days that are used on the internet, streaming media, when you have natural signals like video and audio, or any sort of natural signal like radar, it's all done with lossy compression. And there's a whole theory of lossy compression, which so far we're talking about lossy compression. We've only talked about lossless compression, where we don't actually have a distortion measure as part of the analysis. And you can actually, if you allow for some distortion, compress down to below the entropy. And we want to talk, and how do we talk about that? And that's the whole idea of rate distortion theory. And similarly with communication, you can communicate with error as well if you can go above the capacity to communicate with error. So that's a really, really important topic. If we were on a semester system, that material would be part of the first semester. But because we're on a quarter system, we don't include that in the first semester, first quarter. I think that it should be, it should be a 2-quarter sequence, and you should, in order to get the credit, take it for 2 quarters, because it really deserves 20 weeks. So I hope that encourages everybody to sign up for it. Raise your hand if you plan to sign up for it. That's what I want to see. No, I think you'll really like it. The other thing is it's going to be a little bit less formal. There will be less homework, more paper reading. Okay, so it's not going to be. So this is sort of like a weekly homework thing. Next quarter, we won't have weekly homework, so it won't be as much work. It'll be more sort of for our pleasure. Although the same idea, these slides and the way I'm presenting it will be the same. And if there's interest, I'll do the YouTube thing again. It's a little bit more work for me, but I'd be happy to do that. Is there interest? Are people enjoying the YouTube lectures?
Do you plan to remove the?
I don't know, actually. Part of me wants to, like I've said a couple of times, get them to get at least several million hits or something. But part of me wants to remove them as quickly as possible. Yeah, I probably won't remove them. Actually, I have some other lectures. This is the first quarter that I've done every lecture on YouTube. And I've done YouTube lectures for a couple of other classes earlier this year, but only a couple of times. And this is the first quarter I've done every single lecture. So I think it's kind of nice. I think you guys like it. I don't know. I think all the feedback, everybody keeps emailing me, I'm joking. I haven't heard a single thing of feedback from you guys if you like it or not. But I'm going to assume through as osmosis that you possibly like it. So if you like it, unless someone hates it, in which case maybe I won't do it. Does anyone hate it? So does that answer your question about next quarter?
Thank you.
Okay. So what does?
I like the less homework idea.
Yeah. No, there'll definitely be less homework. Definitely, I can guarantee you that. Usually, this is true for all my classes. The more advanced the class I give, the less homework there is. This is, in some sense, the first quarter is kind of still a core class, and that's why the requirement. So this is more of a traditional class. The more advanced classes are sort of more like seminars.
Are you planning to make it a project-based thing?
I haven't decided. We could talk about that at the beginning of next quarter. If you're interested, we can talk about it and suggest that idea. I think it depends. I mean, if you're actively working in information theory, then I think it makes sense. If you're sort of I think everybody should learn and understand information theory, even if you're not actively working in the core information theoretic field. So if you're not actively working in information theory, it would be interesting to know, like, what would a project be? I want to prove this theorem by the end of the quarter, and then suppose you get to the end and you haven't proven it, or you haven't found a counterexample. What does that mean? So I mean, that kind of thing is a little bit dangerous. If it's something like if it's a capstone-like class for which there's sort of clear, everybody's working on the same project, or something similar, then that makes more sense. But I don't know. We can talk about that at the beginning of next quarter, first day. Okay, so let's do a little bit of background, or a little bit of review. So remember the Shannon guessing game that we played? Everybody had fun, hopefully, last Tuesday. These are not your numbers, I'm sorry, but these are numbers from, at some point, these are real numbers from some particular run of this game. And the idea, again, was that we were leading up to the idea of arithmetic coding, which is what we're going to talk about today. The idea is that we don't send a string of characters. What we do send is a string of numbers, which is how many guesses it took for an entity to guess the correct next letter, where that entity had access to the entire history of letters up to that point. Okay. And then the guesses, if G of T are the guesses, then we said that in some sense, we can estimate the entropy by taking the average log of the guesses. And the reason for that is because the guess at time t is kind of roughly equivalent to the inverse probability of that symbol, the correct symbol, given the whole history. Because on average, it takes roughly that many guesses, 1 over p guesses, to guess something with probability p. So Shannon realized that and said at the time, and figured out that he was able to guess the entropy of English for humans, with using whatever probability distribution or whatever mechanism humans used to determine what the next letter is, including high-level semantic knowledge, like what the words mean and the context in which the words mean things, based on real-world knowledge. And so the humans can go very, very far back into the history of the sentence or even a paragraph. Or imagine, let's say, that you're reading, a 500-page book. By the time you're at the end of the book, you can go back all the way to the beginning of the book, and you're probably very good at guessing. Probably, at the end of the book, you probably have a really good idea what those characters are, because maybe you have gotten at that point used to the language and the style and the word choice of the author. So you can get pretty good. But the other thing that's critical here is that it's adaptive, so that the probability distribution for a given set of letters changes as a function of the history, because we've got this entire history here, x1 through xt minus 1. So something that's very, very probable at one point in time might become very, very improbable at some other point in time, and vice versa. And that's one of the things that makes it accurate. It's not an IID assumption. And because it's accurate, then you can, because it's adjustable, and if it is accurate, and because it's adjustable, you can ideally guess with many fewer, it takes many fewer times to guess the right letter, and therefore you can encode with many fewer bits per source symbol on average. Most of the guys are going to be 1. 1 is obviously going to be the most frequent thing, especially when you get a good estimate of the distribution. So obviously the letter 1, which is going to be the majority of the time, that's going to have only 1 bit, probably. Right? The letter 1 is going to, the number 1 is going to be encoded with 1 bit at a time. So maybe you could get down to 1 bit. Or so this was the basis for arithmetic coding, and we're actually going to talk about that today, the idea of arithmetic coding. Okay, so here's arithmetic coding now. This is sort of, I think the first couple of slides we talked about on Tuesday, but I'm going to go through them again, just to remind everybody, because it's been over a week and a midterm. Actually, I do want to mention something else about the midterm, about the grades. So I haven't finished grading them, and we were going to grade them, but they should be done by the beginning of the weekend, and they're going to be on the webpage. So thank you for sending. There's one person who didn't send their midterm in. Did everybody, raise your hand if you received email from John Soup asking you to upload your midterm to the webpage? You didn't receive email?
I didn't see it.
You don't know if you saw email?
Yeah. I don't think I saw it, so maybe I didn't see that.
Oh, maybe it's going to your spam folder. Are you getting any email from John Soup at all? Can you check your spam box, maybe?
Yeah, I can check.
Okay, because how many emails did you send?
Email by my own account and by Canvas.
Yeah, so basically, this Canvas thing, and I actually checked, I went on the Canvas help system, and I checked, there's no way for us, even though we have, in some sense, God privileges on the Canvas. Actually, we don't have God privileges, we only have angel privileges, which basically says that we can't upload homework for you or assignments for you. We're not allowed to do that. Which means that you have to, we scanned them in for you, actually. John Soup scanned them in, so thank you very much for scanning them in. I think that, but anyway, your grades will show up on Canvas, and only you will be able to see your grades, and also you have a copy of your midterm there as well. So everybody should upload them if you haven't done that yet, or check your spam boxes. 'Cause maybe there's email from us that you're not getting. And then we'll talk about the midterm on Tuesday. We'll go through each problem. Talk about if you have any questions. Spend a little time on that. Okay, so arithmetic coding. Have people heard of Deja Vu, this standard? So this was a standard that actually was developed in the 1990s, and at the time was extraordinarily good, achieved extraordinarily good compression of scanned documents. Talking about scanned documents, when you scan something in, it's not representing it as this big giant grid of pixels. It actually does some very, very smart compression algorithm. It's lossy compression algorithm, but it compresses it down significantly. And Deja Vu was achieving remarkable compression rates, much better than what the PDF standard at the time was doing. But for whatever reason, Adobe at that time was a good company. It's not anymore, but Adobe was at that time a good company and somehow managed to put arithmetic coding into their PDF standard. And now, I don't know if anyone's done any comparison yet between the best compression standard for PDF and Deja Vu. But Deja Vu is still around, and you can still get compressors for it and everything. But it never caught on as much as PDF, as a file format. But Deja Vu uses arithmetic coding. So we're going to assume that we've got a probabilistic model of the source. And what we could do is do what we did earlier, is say, yes, okay, let's say everything's independent. But that's the whole point of what we're doing, is to not have to say that. So in fact, what we're going to do is not say it's independent. We're going to say things are dependent, right? So we're going to say this. We're going to have some probability distribution. Actually, maybe a Markov chain would be something. But we're going to do something even better. We're going to have a distribution, and we'll talk about this at the end of our discussion of arithmetic coding. We're going to have a distribution that does depend on the entire history. And you're going to say, well, how are we possibly going to do this in real life? But arithmetic coders do this. And we'll talk about one family of distributions that are also adaptive, that can do this. So that are much better than just a fixed order Markov chain. Okay, but for right now, let's just assume that we've got some distribution. We'll talk about how that works in a little while, after we understand the method. Okay, so what we do is the following. So we've got this conditional probability distribution, and we use that conditional probability to provide the probability of the next symbol. Okay, that makes sense, right? You've got this history. You don't know what's going to come in the future, but you know what's come in the past. Because remember, what we want to try to do is a stream code. If you've taken signal processing before, in some sense, this is a causal compression algorithm, in the sense that you want to be able to do a good job compressing, but you don't want to have to wait for the end of a block, which in some sense, at any point t, if you're not at the end of the block, you are using the future, right? Because it's not at the end of the block. But on the other hand, you have to wait for the end of the block, and we know that if we can do good compression if we wait for the end of the block, but then we have to suffer this latency. We can only compress things in these blocks. And we want to be able to compress and decompress online as things are going along, for the sake of things like video streaming or audio streaming or other sorts of streaming applications. Communications, voice, telephone, that's the same kind of thing. Imagine if you're having a telephone call with someone and you have to wait till the end of the conversation before you heard the first word. Would that be a very good... What if Skype behaved like that? Sometimes it does. Sometimes Skype does behave like that. But what if it always behaved like that? So that's not good. So arithmetic coding is a method that actually uses the conditional probability, and because it's the conditional probability, it can be, adaptive in this sense. Adaptive in that, we have the probability distribution of a given symbol changing as time increases. It's the same set of symbols. Like here's an example of a set of symbols: A, E, I, O, U, and exclamation point. Usually in arithmetic coding, there's a special symbol which indicates a termination. It's a special termination symbol. So we actually do have to increase the number of symbols by 1 relative to the original alphabet. But that, as we're going to see, is not going to hurt us too badly. So in this particular case, our alphabet size is 6. We've got 5 real symbols and maybe 1 special termination symbol. We're going to see 3 maybe different instances of alphabets. So this is our first example. We're going to change. The first example is going to be A, E, I, O, U, exclamation point. And the next example is going to be just A, B, and box. And then third example is just going to be 0, 1, and box. So just these, we have some source alphabet X. This is our first one. So the source need not be IID. We need not assume it be IID. because we're going to use an adaptive model. And assume for now that we've got this conditional probability here, and this guy is known both to the compressor and the decompressor, or the encoder and the decoder. This is, remember when we did the Shannon guessing game, we needed to have a clone, right? So the clone was somebody who made exactly the same series of guesses. And in this particular case, the clone is going to be this conditional distribution. Now, how does that get there? I mean, this is compression, right? So what you might do, say, is compress something down to a stream of bits, and then somehow you have to say what this conditional probability distribution is, so that when you decompress, it has this. Now, you might think, isn't this going to be giant? Isn't this going to be worse or more difficult than symbols itself? And it turns out no, because what we're going to be doing is we're going to have an algorithmic description of this conditional distribution. It's going to be an algorithm that produces this. And the algorithm is going to be a fixed finite length. So it's just an algorithm that's going to be able to, for any length history, compute the probability. And that's going to be something that's part of the code. It's part of the decoder. In fact, you don't even need to, like when you run gzip, you can't uncompress a gzip file with unzip or whatever, whatever the, with a RAR decompressor, right? It has to be the same encoder and decoder. It has to have a matched encoder and decoder. So the encoder and decoder sort of use this algorithm for estimating this conditional distribution. Okay, everybody happy with that? And this is practical, because this is the intent of this method is to be very practical. So I want to try to, if you've got any practical concerns about any of this, please ask me, and I'm going to try to address them preemptively. But if for some reason I don't do that, please ask. Okay. So in arithmetic coding, remember the Shannon Fan-RLIS coding, where what we did is we took the unit interval. It was a half-Hoeffren interval, and we divided it up based on subintervals of the unit interval corresponding to the probabilities. So for example, if we've got these probabilities, the first, any particular guy might be represented by a particular subinterval. So for example, let's just write this. So this first interval here corresponds to the probability of x1 is equal to a. This next interval corresponds to the probability is equal to e. This one's I, this one's O, this one's U, and this one's exclamation point. And what's being shown over here are these cumulative intervals. So this whole length here, for example, here corresponds to the probability of A plus B plus I plus probability of I plus the probability of O. I realize actually now I'm looking at the slide talking about typos. This isn't really a typo. So in this particular thing, 0 is here and 1 is here. But on future pictures, it's going to be reversed. 0 is going to be at the top and 1 is going to be at the bottom. Okay, so it's kind of like this. I can't really rotate this, but or maybe I can. I'm not going to try. But the point is that we divide the unit interval based on the probabilities. Everybody get the idea? Everybody remember the idea? Okay. So remember, I'll point that out again when we get to these other figures. But what I should do is fix this figure to put 0 at the top and 1 at the bottom. Okay, now here's the trick. Now rather than just doing this at each time and getting essentially a set of bits, what we're going to do is take each subinterval and further divide it into segments of a relative length. So the relative length is going to be based on the conditional probability, which is this. Or we can also think of it in terms of the absolute length, which is this probability. So the relative length, we're going to take like the interval corresponding to x1 and further divide it up into a relative length, based on taking that subinterval, divided up into lengths relative to, proportional to the conditional probability. Or if we look at the absolute length of that interval, it's going to be equal to this joint probability. So the relative lengths could be longer or shorter, because if this is the first length here, and this is the second length, since the conditional probability could be either bigger or smaller than the unconditional probability, the relative lengths could be bigger or smaller. And the absolute lengths are going to be, well, it's probable that the conditional probability is going to have a smaller absolute length, just because usually, a joint distribution over two variables is bigger than a joint distribution over one variable. But the important point here to get is that the relative lengths could change. So here's a picture. And again, unfortunately, I put 0 on the bottom. I really should have put 0 on the top. But it's okay. Just mind that 0's on the bottom here, and 1's on the top here. Okay, number 1. And let's zoom in a little bit. This is so small to see. So basically, we have these first intervals here, right? We divide 0 to 1 up into an interval for A, E, I, O, U, and exclamation point. Let's say that the first symbol is A. Okay? So this is the first symbol. So let's now zoom in on A. And you can see, if you zoom in on A, that that length is divided up into further subintervals corresponding to this stuff down here. Right? So because I don't like zooming, or actually I do like zooming, it's kind of fun, but that when we expand that out into here is sort of the relative, it's another thing. So this is no longer 1, and this is no longer 0. This becomes the probability that A is equal to, the x1 is equal to A, and this becomes 0 still. But the point is that interval is further subdivided. And maybe the next symbol is E. So now there's E, which is further subdivided into more relative lengths. And then then we get this next interval here. All right. So here's the first interval, the next interval, and then the third interval, and so on and so forth. And we keep subdividing these intervals. And again, if we look at, let's zoom in on this second case here. Okay. This absolute length from here to here is equal to the joint probability of A and E. So the relative length is 1, because the probability of, if we sort of further subdivide that for the next guy, the relative length for each one of these little guys is 1, but the absolute length is just P of A, comma E. Does everybody get that? Kind of what we're doing here? So as we keep going, we just keep, further subdividing and subdividing and subdividing. And it all depends on a particular string, because remember, we have a particular source string that we're trying to encode, which in this particular case is a string of symbols from this alphabet A, E, I, O, U, and then at some point when we reach the exclamation point, that's basically an indication that we're done. Nothing else happens after that, and we've ended. Yep.
Why is that the condition?
Well, because remember, the conditional is something that is between 0 and 1, right? So, the way to think about it is that we've got, let's write it up here. We've got the first subinterval is P of A, right? And that's this guy down here. The next one is going to be the probability of, and so that P of A, we have this interval corresponding to this. So that whole length, this whole length here is P of A. Let me write this down at the bottom. The length is P of A. Maybe I have this somewhere written. So that length is P of A, right? But now this whole length here is P of A. Oops. Because we're just zooming in. I mean, I can zoom in on the iPad, but I'm actually zooming in on the figure. So that whole length is P of A. So now this relative length here is, we've got P of E given A, the relative length here, right? But then it's P of E given A, which is a fraction of a totality. We multiply it by P of A. So the real length is P of AE. So I should say, we should say, here, make sure that this is clear, this is the relative length. Actually, let me draw it in a different color because it's getting confusing. Hold on. confused with all of this stuff going on. So, just so that's very, very clear. So this is the relative length is P of E given A. We got this is the absolute length. Does that make sense? Okay. And so on and so forth. So basically when we get to this guy over here, that's also an absolute length, but on the third guy and the fourth guy and fifth guy. Hope that's clear for everybody. So we don't need this stuff up there. Let's move on to the next slide. So I think this is something that we've already said in the slide, that the I wonder if there's a way of turning off these things to make you so you can see this thing. But does that look a little bit better? Yeah, it's like shining lights right on the projector. That's not good. Okay, so all right. So now I don't think we ever had that light on before. I don't know. But in any event, so we already talked about the absolute length of the interval for AE is this, and so this is really the absolute length. Right. So the other point to note is that the intervals are getting smaller. In fact, they're getting exponentially smaller as n goes by, because each time we're multiplying it by some number less than 1. So these guys are getting small very, very fast. We've already said this, the relative lengths, the conditional probability, the relative lengths can change. But what's critical about this, when we look at, as we will see, the binary expansion, the number of additional bits to specify these relative subintervals in general is not going to be changing. We just need to sort of add additional bits after the binary point. Right? Add additional, but we're not. But if we have a pretty large relative length, then we need to add few relative bits. If we have a small relative length, we need to add a lot of additional bits. That's the idea. So that, but on average, on balance, like the average number of bits needed, like in particular, if the relative lengths stay the same, the number of additional bits we need to stick at the end of this binary expansion of the number is going to be constant. Right? And we'll see that in a minute. Maybe I should make that point and add that to the slide, because that might be an important point. The number of additional bits needed to specify a relative subinterval is approximately the same, and it's exactly the same if relative lengths are the same. And relative lengths are the same means that the conditional probabilities are not changing. I'll add that as a bullet point. Okay, so yeah, I think I've already said this too. So at t is equal to 1, the relative interval for A is p of A. At t is equal to 2, the relative interval is p of A given whatever the symbol was for the first random variable. Now, what I haven't said is, I mean, we know the idea of Shannon-Fano Elias coding, but that uses the same intervals at each step. Here we're using different intervals at each step, depending on this conditional probability. So if the symbol gets very, very probable, the relative interval is going to be much larger, and it takes fewer bits to make distinct. Whereas if a symbol becomes very, very improbable, we're going to use a much smaller relative subinterval, which means that the number of bits needed is going to be much larger. So we're going to use more bits for the things that are more relatively probable or conditionally probable, and fewer bits for the things that are, did I say more bits? We're going to use fewer bits for the things that are more conditionally probable, and more bits for the things that are more conditionally improbable, which is exactly what we want to do when we've got a conditional probability distribution. So, so here's what we're going to be doing. We're going to be essentially encoding these probabilities. So with these half-open intervals, and by half-open intervals I mean these sorts of things. So we've got a binary point and then a bunch of bits thereafter, which specify an interval. And it's always going to be the case that we're going to take this last bit and add, this is going to be 0.0110 plus 0.0001 to get the open side of the interval. And so that's going to encode all strings that begin with this, right? 0110. And the other thing to say is that that interval, that with more bits, corresponds to a shorter distance than this interval here. You can't see that. How about now? Than this interval here. Right? Okay, so how do we actually then code? Let's make this more formal. So let's say that I is the current source symbol number for x of I. And so we're going to compute these quantities. We're going to have a lower interval position and an upper interval position. And all this is going to do is going to, the lower position, which is going to be smaller. We always have, obviously we're going to have L of n is less than U of n. And it's going to be strict because of the fact that we're going to assume that, actually, well, I should say less than or equal to. We could have zero probabilities. Sure, why not? Let's just say it's less than or equal to. L of n is less than or equal to U of n. And the reason for that is because U of n is just equal to L of n is equal to L of n plus P of x of n is equal to J, given history. Right? So U of n is always bigger. Does everybody see that? We're just summing up the first I guys, or the first I minus 1 guys, so it's conditional probability. So on arrival of the nth input symbol, we divide the previous interval. The previous interval is divided by L of n and U of n, and it corresponds to this half-open interval. Right? That's basically the picture that we drew. And so we're going to divide that half-open interval, L of n and U of n, into parts depending on the probability of the current symbol. Right? So here's how we do it. So here's a specific example. So let's say that we've got L of n, L of 1 and U of n. Let's just talk about the first guy. So using that, that picture that we saw earlier, the first interval, which corresponds to A, is going to be the interval between 0 and probability of x1 is equal to A. The next one is going to be, it's going to have a lower value of probability of x1 is equal to A, and upper value of probability of x equal to A, and probability of x equals B, E equals E. And so on and so forth. This is probability of A and plus probability of E. And this is probability of A plus E, probability of E plus probability of I. And in general, here's the lower one and here's the upper one. And then the very last one corresponding to this exclamation point is going to be the probability of all real source symbols up to 1. Remember, they're always open on the right and closed on the left. Everybody with me? Okay, and here's going to be our algorithm. And what this algorithm is going to do is essentially define the upper and lower values for these intervals, L and U. And L and U are going to be time dependent, but we're just going to use the same variable in this algorithm. This is how you might code it up. If you had, these things are going to get small. So assuming that you could have representations of probabilities that could get this small, and we wanted to send n source symbols, we might try this algorithm. So we start by initializing the lower value is equal to 0, the upper value is equal to 1, and then the interval, or the probability, in this case, is u minus L, which in this case is just 1. So then for all of our source symbols, we've got n symbols, or this is the total length of the set of source symbols that we're trying to encode. What we do is we first we just compute upper and lower at time n, as we did in these equations. These are the equations that we saw here. Wherever it was, here. So we compute lower and upper in this strategy. And then what do we do? Where's the algorithm? Here it is. Okay, so then we scale the upper and lower. Because remember, these are based on conditional probabilities. We scale them by the interval p. So remember, the upper and lower are sort of relative intervals because they're based on the conditional probabilities, but they need to be scaled to be into the range of the current interval, which is p, and the absolute length of the current interval is p. And then we just shift them by the lower part of the current interval. And so now we have a new upper and lower, and then we define the new interval length. And so that picture that we saw going horizontally from left to right, this algorithm does exactly that. Okay? So if you understand that picture, you understand this algorithm and vice versa. Any questions? Okay, we do this, then eventually we get to this exclamation point. We're all done, or we've got n symbols. Then we've got a final interval. Then all we need to do is we need to send any binary string that lives with us in that interval. And we're done. That becomes a code for the set of source strings. Okay. Now you might say, great. In fact, you could use the Shannon length. You could use, that probability seal of log of 1 over that probability plus 1, and that you get something that gets the entropy rate of the source. But you'd be done, right? And you'd be happy. Would you be happy? Raise your hand if you would be happy. If you are happy.
Can you say the question again?
Are you happy?
I need more redundancy.
If this was true, would you be happy? No, the question is, if you were to do exactly what this step says, which basically says you compute the final interval, upper and lower, and then you find some binary string that lives within this interval, and maybe you truncate it using the Shannon length, and then that becomes the bit string. Very similar to Shannon and Fano-Elias coding. We're dividing these intervals between 0 and 1, and we're looking at the binary encoding of these fractional numbers between 0 and 1. And if you sent that binary string that lived in that interval, would you be happy? Once you've finished computing this final interval, would you be happy? That's the question. And the answer is no, you would not be happy. Why? Because you wouldn't have achieved a stream code. The whole point of a stream code is you don't want to have to wait for the end of the stream to send a bit string. You want to be able to send bit strings as you're going along. So you would be quite unhappy if I told you that I was going to give you a stream code and this is what I did. So I can predict when you're happy and when you're not happy. So right now, if this was the case, you would be unhappy. But you're not going to be unhappy. You're going to be very happy because this is not going to be the case. Okay. So let's see why you will in fact be happy. Because we want to make the algorithm online so that we start writing out bits as soon as we know the interval. Or at least we know something unique about the interval. And in fact, as soon as we know that all intervals that it might be must start with a particular bit string, we can start writing out those bits. We don't have to wait till the end. And in fact, we can figure that out as we're going along, computing these intervals and these subintervals and these sub-subintervals and sub-subintervals. We're going to be in an interval where everything between the upper and the lower, or I should say between the lower and the upper, everything between the lower and the upper has to start with this bit string. So as soon as you know that, send those bits out and start compressing. So similarly, if the current interval is this, I can send out the prefix 1001 because I know that nothing will ever leave that interval. I mean, maybe I'm going to refine that interval further by making it smaller and smaller, but I know that anything beyond is going to. This is a half-open interval. We can never get bigger than or equal to this value, and we can never get smaller than this value. So if I send out 1001, I'm done. Or at least I'm done with those first 4 bits, and I can keep going. So here's an example. So to specify all these conditional probabilities, I would need a big giant table. So I'm only going to specify the probabilities for the string that we're going to encode. And the string that we're going to encode is this string. It's BBBA box. And box is now the exclamation point. Why box and not exclamation point? It's been changing notation. But it's not so bad. Box is our special symbol now. And we only have two symbol alphabet, A and B. And we have box, which is the special terminate symbol. Okay, so what we want to do is we want to encode the string BBBA box. And here are the probabilities. So the first set of probabilities, we have probability of A is equal to this, probability of B is equal to that, and then probability of box is equal to that. The next set of probabilities, we're just going to give you the conditional probabilities, which are these guys. Let me use a different color, just for variety. And here's the third set of probabilities. And do I need to read them out, or does everybody understand what's happening? These are the conditional. We're specifying conditional probabilities, and we're only conditioning on that which we know to be true of the source up to that particular point. So like, for example, in this third case, the history is BB. So the only probabilities we're going to need are the conditional probabilities under the history of BB. And similarly, for the fourth symbol, the history is BBB, so I only need these probabilities. Those are the only ones that matter to specify the relative subintervals. And lastly, once I've got this history of BBBA, then I've got that set of conditional probabilities. Yeah.
What would happen if you give the block probability 0?
So if a particular symbol has probability 0.
Well, like the termination symbol, because it can only appear once, and we know it has to be a closed interval. Or if we make it just be that closed interval.
Yeah, we can't give it a probability of 0, and here's why. Because remember, this is sort of something that specifies a way of encoding any source string. Okay, any source string I might encounter. So we're designing the probability model not based on the source string that we're going to get at any particular time. We're designing it in a way that gives us a source string that abides by those probabilities. So if it was the case that we gave it a probability of 0, then it would mean that can't happen there. That the termination can't happen. And if that's what is true of the true source distribution, fine. I mean, that would be no problem. It would mean that there's no interval dedicated to the termination symbol at that point. But if we then encountered a symbol, a termination symbol at that point when we had a probability of 0 for that termination symbol, we wouldn't be able to encode that. It's very similar to saying if you've got a code for a source alphabet and we get a symbol which is not in the source alphabet or that has probability 0, we suddenly use infinite length. And we just don't deal with that. We can't deal with that situation. So in some sense, we can never give it a probability of 0 unless we're absolutely certain to know that that's the true source symbol, or we have some failure mode or recovery mode or some back-off probability model to sort of readjust our probabilities based on being wrong about our assumptions about the source. Because you know that, for example, in general, in real life, we never have the true probability distributions. We have something approximate, and we pay a penalty, which is KL divergence. And that's not true. That's true in this case as well. So we can do an analysis in this case, in which case we'll see that in each case we'll be paying KL divergence per source symbol, but in this case it's going to be adaptive. It's going to be a sum of KL divergences for each source symbol. And if we have the probability is 0 and we get something that's not, then the KL divergence in that case is going to be infinite. And because it's the KL divergence of what? D of PQ. So if P is not 0 and Q is 0, it's log of something divided by 0, which is infinite. Okay, so let's, for the moment though, assume that our probabilities are correct. Okay, but that, just for the analysis right now, let's just make that assumption. But again, they're adapting. They don't have to be fixed. So, okay, so we get these probabilities. And what we're going to do, after we're done doing this procedure, we're going to get a final, that's a good question, by the way. I liked that question. So we're going to get a final interval corresponding to BBB8 box. Right? And here's BBB8 box. So let's talk about this picture for a minute, because we're going to be seeing this picture. And it's definitely a little bit confusing when you first see it, but at the same time, it's actually extraordinarily useful in understanding arithmetic coding. So this is a picture, and now what's going to happen is 0 is going to be at the top and 1 is going to be at the bottom. And these are intervals. Because this is going to be the interval, the final interval here. So what do we mean by interval? This is, so it's going to be a half open interval. So it's really going to be sort of closed here, open here, and this is going to be this. And so 0 is going to be up here, and 1 is going to be down here. And we're talking about half open subintervals of the 0, 1 line, right? Actually, I should do that in color. When there's color, use it if it's usefully informative of what you're trying to talk about it, but don't overuse color. I hope that I never overuse color, but I use it informatively. So basically, this thing here, that corresponds to the interval that's computed for BBBA box. Now, what's on the right-hand side are intervals corresponding to fractional binary expansions. These are also half-open intervals. So, in the sense that this is closed here, and this is open here. And this corresponds to all bit strings that begin with the string 1, 0, 0, 1, 1, 1, 1, 0. Okay? Now I think a couple of other things I wanted to say about this. So, oops, we don't want a stripe, we want a page change. So they're half-open subintervals of 0, 1, with 0 at the top and 1 at the bottom, because we swapped relative to the other figures that we were doing. So 0's on the top and 1's at the bottom. On the left, which basically means this stuff over here, are intervals LU, half-open intervals again, LU, corresponding to the string made according to the conditional probability distributions. Okay? On the right, we're going to see intervals that have this form. So there's going to be some bit string, B1 through BK, and that's a bit string, and it's going to be represented by this interval, 0.b1 through bk, comma, 0.b1 through bk, plus 2 to the negative k. Okay, that's exactly what we did. We're just going to add 1, and we're going to be half open on the right. It might involve a carry, it might not involve a carry. Like, for example, in this case, here, this is a sanity check. If we add that to this, does this involve a carry? No, it doesn't, because we just set the last 0 to a 1. Remember, if that's not clear, I should really... I know this is confusing. So try to... this interval That's a half-open interval. This number that's represented here, we're going to see a lot of this. This point here is going to correspond precisely to this bit string. And then this point here corresponds to that bit string plus, is this plus 2 to the negative k. But we're open at that point, because we're open. Okay? So this whole interval, though, from here to here, corresponds to this bit string. It'll be more clear maybe when we look at the whole picture. So then the final code word is anything that lies uniquely within that subinterval. In this particular case, the code word is going to be 1, 0, 0, 1, 1, 1, 1, 0, 1. And then why is that? Because, let's zoom in on here again. The final code word is this, right? And that corresponds to this little tiny subinterval here. Oops, we don't want that, we want this. This little tiny subinterval here. Again, we're sort of closed here and open here. I can't zoom in that far on this tool. Oh no, I can, a little bit more. So there we go. That's as far in as I can zoom in. That string, which is down here, this string which is down here corresponds to this interval which is up here. And notice that that entire interval, let's erase this a little bit. This entire interval here lives within the interval corresponding to the string we want to encode, which is BBB A box. So what we need is for this interval to live entirely within this interval. And then that will, by using that bit string, make sure that we can determine the interval where the final encoded string lives, which is this guy. Okay, so let's look at the entire picture. The entire picture really looks like this. By the way, I should mention that this is actually from Mackay's book. But he didn't annotate it other than essentially doing this. So what we're going to do is we're going to annotate it a little bit in the following way. When I did this before, I've done this before, I actually had to zoom in. Now with the iPad, I can actually zoom in. So let's first of all look at a couple of points. So first of all, like I said before, 0 is at the top, and 1 is at the bottom. And the whole thing corresponds to this half-open interval, which is closed on the bottom and open at the top. Right? Oh, sorry, well, closed at the top and open at the bottom. Closed at 0, open at 1. Okay. So when we consider the string, let's zoom in a little bit on this. So consider the string 0, just the bit 0. We're talking about an interval which is closed. We're talking the interval from 0 to 1/2. We're talking about this guy. So the bit string 0, which is just one symbol, corresponds to half-open interval, which divides it in half. Right? So 0 corresponds to that interval. And 1, just the bit string 1, corresponds to the interval which is closed at 1/2 and open at 1, and this interval here. Right. Similarly, or I should say recursively, if we divide this half-open interval, so now let's put this half-open interval back, which is closed here and open here. So all strings that begin with the bit 0 must lie within that half-open interval between here and here. Now all strings that begin with 0, 0 must lie within this half-open interval here and here. Right? And all strings that begin with 0, 1 must lie within this half-open interval 0, 1. Except that should be half-open. And similarly, all strings that begin with 0, 0, 0 must be in this half-open interval here, here. And all strings that begin with 0, 0, 1 lie within this half-open interval. And all strings that begin with 0, 1, 0 lie in this half-open interval. all stringless. And so do you get the idea? So this sort of keeps going on down until we sort of get to this stuff over here, where the intervals get very small very fast. And then this is showing exponential decrease. Now I would run out of pixels very quickly on even my retinal display iPad mini, which it's not, but if it was a retinal display iPad mini, I would run out of pixels very quickly. Maybe with a retinal display, I would be able to go maybe down 1 or 2 more levels, but because of the exponential decrease in interval size, even like your favorite Nexus 5, whatever, with 332 pixels per inch density on your tablet, wouldn't be able to resolve these intervals very soon. You guys are not tech gadget junkies, I can see. Is anybody a tech gadget junkie? My nephew is a tech gadget junkie, so had he been here, would have laughed at that joke, but it's okay. I thought aren't all EE people tech gadget junkies? No, you're not. You just like wires and resistors and capacitors and stuff. Or? No. Okay. I promised you I would never tell any jokes anymore. So anyway, let's just get to the point. Do people understand this picture? On the right-hand side, we're creating intervals corresponding to binary expansions after the binary port. On the left-hand side, we're doing the same thing, except we're dividing intervals corresponding to the string. So on the left-hand side, like if the first string was A, we would have this half interval. If the first string was B, we'd have this half interval. Or it's not a half interval anymore. It's a relative interval. And if this first string was box, if the first string was this termination, we'd have this relative interval. Now, since we're encoding the string B, 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 A box, the first letter is going to be B, so we immediately start looking at that relative interval, and then we need to divide that. So we know that we're in this yellow relative interval. If the second symbol was A, we would be looking at this relative interval. If the second string was box, we would be looking at this relative interval. But in fact, the second symbol is B, so now we're looking at this relative interval. Similarly, if the third symbol was A, we would look at that relative interval. If the third symbol was box, we'd be looking at this relative interval. But since the third symbol is B, we're looking at this relative interval. And the fourth relative interval is going to be this one. Right. Oh, no, that's wrong. Fourth relative interval is going to be this one. You can see how small it gets. It's going to be that one, BBBA. And so what we're going to do then is blow it up. So the interval corresponding to this guy here is going to be blown up to correspond exactly to this. Okay? Does everybody get that? So now we're blowing that up to get this right-hand side thing. So let's now blow up on the right-hand side. And so we can continue along if I guess now what is it? It's the fifth symbol. If the fifth symbol corresponding to A would be that guy, if the fifth symbol corresponding to B, to box, it would be this guy. Sorry, B, it would be this guy. But because the fifth interval corresponds to box, it's this guy. And so now I think it's actually worth going on to the next page because I have a blown up version of that. So this is just basically what we're going to look at now is just this stuff here, but blown up. Okay. So here we are in BBBA box. And we have this interval corresponding to BBBA box. And here's this string which corresponds to this whole interval. Could we send that string, the one I just circled in green? Would that be valid? No, because it doesn't uniquely specify this interval. We have to do one more subdivision. So if we take this thing I circled in green and added, 2 to the negative k, where k in this case is 2, 3, 4, 5, 6, 7, 8. If 2 to the negative 8, I would get this guy. If I added 2 to the negative 8, aren't you glad you can see all this on YouTube? 2 to the negative 8, you get this guy. That's also no good. The reason why the first one isn't good is because we have overlap here. The reason why the second one isn't good is because we have non-overlap there. So therefore, what we have to do, in order to specify a binary string which corresponds to the interval precisely corresponding to the source string, we need to go down to this interval here. And the way to do that is to take this string and how do I divide that into two intervals? I need to append either a 0 or a 1 to that. And so what I've done is I've taken that string here, or I should say David Mackay has taken this string here, which is 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, and I've appended on a 1, because that corresponds to the second half. If I appended on a 0, it would correspond to this interval, but that one's no good because of this overlap here. That we can't have. If I append a 1 at the end, it corresponds to this interval. And that's the one we want, because that interval here is fully contained within this larger interval here. I have to tell you, this is the best explanation of this I've ever given in my life. So if this is confusing, it's just naturally confusing. So I think that if you go back and watch this, I'm recording this for your sake, if you go back and watch this on YouTube, or maybe read it and then watch it, or maybe that's probably the best thing, is to read it and then watch it. The problem with watching is that you'd have to suffer through these non-funny commentaries. But it is a little bit confusing precisely what's happening, but this really does describe what's going on. So don't be too uncomfortable if it's not clear, but please do understand it, because you need to understand it. So I think I already answered this question, but can I ask it again? Why can't we use 1, 0, 0, 1, 1, 1, 1? Where is 1, 0, 0, 1, 1, 1, 1? Why can't we use that guy? The answer should be here. Well, which guy corresponds to that? If you had a laser pointer, you could tell me. 1, 0, 0, 1, 1, 1, 1 corresponds to this interval. Right? In fact, if we zoom in, I think you can even see it. It's in yellow. 1, 0, 0, 1, 1, 1, 1 corresponds to this guy. Does that interval live within this interval here? No, obviously not. We need to choose a binary expansion that corresponds to an interval that lives strictly within. I mean, remember, it's closed on the bottom, open at the top. So we can actually be, if we happen to be lucky, and this guy, the bottom one, the one closer to 0, corresponds to something closer to 0, then yeah. But on the other hand, that's unlikely unless we have like d-adic distributions or something. Which I should say 2-adic distributions, which we usually don't have. So the picture as described is kind of accurate, because you can see that what's displayed is that this guy is supposed to be a little bit bigger than this value here. And clearly this value is smaller than this value here. So this interval is then fully contained within this interval. Okay. So why do we care about this interval containment? Because that gives us a prefix key code. Nothing else can be there. So as soon as we discover an interval, like going back to this picture, as soon as like this green subinterval here on the left, as soon as we know that it's this green guy, we know that we're corresponding to this whole half, and so we can send a 1 out right away. because this green interval here disambiguates the very first bit. So we can send that 1 because we're never going to jump from this green to somewhere over here where the first symbol would be a 1. It's not going to happen because the green guy, we can only be a subinterval of the green. And remember, these intervals on the left are going to get smaller and smaller and smaller. So remember, first there was the yellow interval, and then there's the green one, and then there was this, what looks like tan to me. Then there was this blue one. As soon as we know those intervals, then we can, as long as there's some binary string whose interval is fully contains the interval that we know we must be in, we can send it out the prefix of those binary of those bits. And hence it's a stream code, so you'll be happy. That was the definition of your happiness. Remember? That is the stream code. So this is a great picture. And I can't take credit for this picture. This is, again, from David Mackay's book. He's the one who came up with it. It's my fault that I swapped the zeros and the 1. Those were my figures. So I should have put 0 on top. Actually, I think he should have put 0 on the bottom. I think that would have been more natural. Usually 0 is less than 1. I don't know. Maybe he's from Australia. Actually, he's not. He's from England. I've probably made this joke. Every time I teach a class, I make the joke about Australia. That in Australia, in the northern hemisphere countries, we always have figures where you're going from left to right. Like we have figures that sort of have these Markov chains look like this. Did I already make this joke in this class? Okay, well, that's a Markov chain in the northern hemisphere. When you're in Australia, a Markov chain looks like this. Right, going from right to left. In the northern hemisphere, we put 0 at the bottom and 1 at the top. In Australia, or if you're David Mackay, you put 0 at the top and 1 at the bottom. Actually, I know David Mackay, so it's okay. Maybe he'll someday listen to these lectures. No, that's not going to happen. Okay, so how do we do decoding? So we basically run that same algorithm that we saw before, except we do a little bit differently. We continue along until we find this special symbol box. And while we haven't found that yet, we compute L and U. And we find an I. Is there a bug here? Yeah, I think this should be the this is the that's right. Okay, so alpha is this if you're getting what this means. Okay, so here's alpha. Alpha is this binary string. So we've got this prefix stuff, and we find an I that in some sense includes the binary expansion of the bit string that we want. Okay, and then once we found that I, we're guaranteed to find it because we're using half-open intervals. Then we update our upper and our lower and our interval, and then we repeat. And that gives us a new bit string. And keep going. Okay, so maybe this is a good time to take a short break because I've kind of used up the first half of the lecture on this. Because this is taking a long time with arithmetic coding. So let's take a short break and give people a chance to rest, and we'll start again in a little while. Okay, we're back. Now, the issue, I mean, especially since today we want to try to talk a little bit about practical issues, is that this interval is going to get very, very long, or I should say small, and so therefore the bit string corresponding to it is going to get very long. And it might even be a repeated number or an irrational number or something. And we only need to send a long enough string to uniquely identify the string of source letters. And so what we could do is, for example, define f, which is the average of the upper and the lower, and then define this sort of truncated average where L is essentially the length that we send, and where we maybe use a Shannon-like length, where at each stage we send. Now this is something that allows us to determine the sort of additional set of bits that we use. We don't actually use this to make to say what strings we actually send. This is just to compute the final length, and then we sum up all of these lengths, something like that. But the problem with that is that we're going to be paying potentially one extra bit per source symbol again. And so in order to analyze the lengths, we're just going to, for the length analysis, we're going to look at the Shannon length of the entire code. So like, here's the idea. So we're not, as we disambiguate the bits, as the source symbols come in, we're getting smaller and smaller and smaller intervals. Any bit that is unambiguously going to be sent gets sent right away. Okay. At some point or another, we're going to reach this termination symbol, and we're going to be able to estimate this 1 over log of p of x, right? And the reason why we can do that is because this is equal to the probability of x1 times the probability of x2 given x1 times the probability of x3 given x1 and x2. Since we have all of these conditional probabilities, we just multiply them all together. And then the final number of bits that we send is going to be 1 over p of x1. Let me just write this down. P of x of 1 through n is equal to the product over I of p of x of I given x of 1 through I, x of I minus 1. All right, so we just take the product of that, compute that, and then use the Shannon length on that thing. And that's when we decide how many additional bits to send. Like we've counted how many bits we've sent already. They've already been sent out, and maybe somebody's been watching that movie at home on Saturday night. But then when we want to send the final set of bits, we just use this length. So, oh, we've already sent this many bits. Here's how many more bits we need to send, and then we're done. And that's how we decide how to length. And then what that's going to do is make it really easy to analyze in terms of the rate of the code in terms of average number of bits per symbol. So the expected length is going to be expected, it's the sum over all strings of the probability of that string times the length of that string. And here we're just going to get back exactly the same analysis that we did before. And I'm not going to go through it, but we end up getting is the entropy of that source. If assuming the conditional probabilities are correct, we're going to get the entropy of the source plus 2. And then when you divide by n, we look at the number of bits per symbol. We're going to get the entropy rate of the stochastic process. But note that this is true, this is the entropy rate. We don't need we're not encoding things by blocks, we're encoding things by streams, but we're still using a block-like analysis for determining the expected number of bits per symbol. Right? Now, but what it does do is it means that as the stream gets longer, we're going to get closer and closer to the entropy rate. Right? But that's okay because we expect this stream to be very long. I mean, if it's a movie, we're going to have hundreds of billions of bits or something. And most symbols are going to be, there's no blocking necessary. The blocking is done implicitly via the conditional probability estimations or distributions that we've got. Yep.
If we can send bits by bits, then why do we need the blocks?
Because we still need to be able to determine what the final symbol is. We need to have a termination. Because otherwise, let's say, we need to be able to say when you're decoding, okay, this is the end. I guess what you could do is you could just have it, have it end, but then somehow you need to know the length. You need to send the length. This way, basically, you don't need to have any, like the decoder can start decoding without actually needing to know any length. It can sort of keep decoding and decoding until, oh, I decoded this symbol, that means I'm going to shut down the channel and assume it's over, and I'm done with it. And we're not going to, the conditional probability, as long as it doesn't give them too much probability for that, it's going to give us the entropy.
Essentially, this the symbol happens once in all sessions.
Yep, only happens once.
We go back to the same question that he asked. What's the point of assigning probability for it?
Well, we talked about that. The point is that if you know that it will never happen at a particular point, you don't need to assign any probability for it.
Which we know already, right?
Well, that's what I'm saying. If you know, then it's okay. If you make a mistake, you will pay a penalty. So if it's the true distribution, I mean the true distribution, and you know that no stream is going to be shorter than 100 symbols, yes, you should assign 0 probability to it up until 100. Okay, your model of the conditional probability. In real life, we don't have the true distribution. So we always need to add some tiny little probability for it. It's an extraordinarily improbable event. So we give it a tiny, tiny, tiny probability at each time. So we're actually not taking away a lot of the probability from all the other symbols. Maybe we take some tiny, tiny probability, and maybe at the very end, okay, we pay that once. We pay that little bit extra bit. But that doesn't matter, because as the stream gets longer, the length of that additional cost is going to go to 0 as the stream gets longer. So it really doesn't end up costing anything. And if you are absolutely certain that anything you encode with, like let's say you are designing an encoder, a streaming encoder for movies, and you know that no movie is shorter than 2 hours and 20 minutes, or whatever the length of your shortest movie is. So then your conditional probability table that you use for the encoder and the decoder should indeed give you 0 probability for that, because you know that you're never going to see that. But on the other hand, if you're encoding it for anything, and you might have like 50 microsecond long movies, you can't do that. I don't know of anyone who enjoys 50 microsecond long movies, but who knows? Maybe somebody likes to watch a lot of movies, and so they only want to see the 50 microsecond versions of them. Imagine seeing the 50 microsecond version of Star Wars, for example. What would that be? I don't know. Maybe the problem is, like, since I have little children at home, a 3-year-old and a 6-year-old, and maybe since having little children, my humor has sort of digressed to the 3-year-old, 6-year-old humor, and so maybe all these jokes, I know they would laugh at these jokes, so maybe that's what's going on here. That I'm giving jokes for 3-year-olds and 6-year-olds, and I have to get used to graduate students again. So, okay, so the other thing that we haven't at all discussed is, especially with regard to practical issues, is estimating these probabilities, these conditional probabilities. So we've been assuming that we have them. We want to have an adaptive model. Obviously, we can't use the true distribution because the table sizes for this get exponentially large. And that's the whole point of, or the whole problem with block lengths, especially when you have things that aren't IID. I mean, so one thing you could do is, let's assume it's IID, but that's obviously not adaptive. So we want to have an adaptive model. So we can't assume it's IID. So how about something like this? Like, here's a nice model. It's a very simple model. It's a Dirichlet probability distribution. And it doesn't have any independencies at all. It basically says that the probability of symbol A is equal to the number of times I've seen A in the history plus some additional alpha. We need to, alpha is always going to be greater than or equal to 0, divided by the sum over all symbols and the number of times that we've seen that symbol in the history plus alpha. So if alpha is strictly greater than 0, we're never going to get anything that's equal to 0. So basically it says, it's sort of using the history, and it says, well, if I've seen something frequently, I'm likely to see it again. And if I've seen something infrequently, I'm likely to see it again. Another possible model is like you could have some sort of decaying average. Like you could say, you could count the number of times you've seen A, but as you move away from the current time, you could decay, kind of like an IIR filter or something. So but here you're taking seeing an A at the very, very beginning and seeing an A very, very recently gives us the same count. But it is adaptive, right? Because if I suddenly start seeing lots of a particular symbol, then it increases my probability for seeing that symbol. And everything that I've seen matters, right? So it's no conditional independence. What do you guys think about this distribution? This conditional distribution. It's quite reasonable, I think. Certainly human language is like that. If I use a word like Tuesday, it's very likely I'm going to say the word Tuesday again. Even though maybe I haven't said the word Tuesday this entire lecture, I've all of a sudden started using the word Tuesday quite a bit. And you're probably thinking about the word Tuesday. And I could say, don't think about the word Tuesday, and you're still going to think about the word Tuesday. So now I've said the word Tuesday. Every time I say the word Tuesday, I say it one more time. So I've said that word now 7 or 8 times. And so you're probably expecting me to say the word Wednesday. Tuesday. You're expecting me to say Tuesday again. So that makes sense in many, many streams. Small alpha, they said, what does alpha mean? So alpha is sort of how quickly you adapt. I mean, if alpha gets very, very big, it's kind of like a uniform distribution. And you sort of slowly adjust with respect to the uniform distribution. But if alpha is small, you adapt very, very quickly. But again, you could imagine some decaying exponential thing where you weigh recent things much more frequently than far things. That would be another strategy. Large alpha means sluggish. So should we do this? So the question is, how do you derive this? I was going to do like this Bayesian derivation of this distribution, but maybe I shouldn't do this. Maybe I should skip it. The point is, you can derive this distribution using a Bayesian rule. I mean, in fact, we're just going to derive the Laplace distribution here. I don't think it's worth going through this because I'd like to at least begin channel capacity a little bit because that's an important topic. But let me just end up with this is the end of. So the stuff I've skipped is just how do we derive that distribution using Bayesian reasoning. But it's not necessarily the distribution that people use. People use more sophisticated adaptive distributions. But you can get the idea now that, however, that it's not crazy. You don't need an exponential amount of space to store a distribution that's adaptive and has no dependencies, no independencies. Like in other words, it uses the entire history. Because you're not keeping the entire history, you're keeping a statistic about the history, like the number of times that each symbol has occurred or something like that. So you only keep a vector which is of length equal to the alphabet size rather than the history. Which basically means that there could be very, very different histories that give you the same conditioning. Like, you could take any permutation of your history and you're going to get the same vector. The same vector of counts. But maybe that's good enough. There's another thing that I should mention about practicalities. These intervals, in order, like these algorithms, you have upper and lower and the interval length. Those things are getting exponentially small. Now, if you were to implement this in finite precision arithmetic, like 64-bit floating point arithmetic, you'd very, very quickly run out of precision. Right? So when you implement this, and I think I'm going to ask you to implement this in MATLAB, you're going to have to think about how to do it, because you're going to need to come up with a representation of numbers where you can actually have this enormous dynamic range, where essentially only the exponent is decreasing linearly in the length. Right? So what's the smallest number you can represent with 64-bit floating point numbers? It's about 10 to the negative 285, I think. And the smallest number you can represent with 32-bit floating point numbers is about 10 to the negative 35. So as soon as the exponent gets bigger than 35 for single precision, or I should say gets smaller than negative 35 for single precision, or negative 285 for double precision, you're out of luck. You just can't represent numbers anymore. So you have to do something different. So one way of doing it would be to only represent the exponent, which basically means that you represent your numbers in log space. All numbers are really log of those numbers. Another way is to somehow divide and normalize each time you're renormalizing so that you're still always dealing with numbers between 0 and 1. And so the upper and lower get scaled. And maybe you can do it that way. So you guys are going to need to think about this when you implement it. Okay, any questions about arithmetic coding? Okay. Any questions for you listeners on YouTube? Wouldn't it be great if you could time travel back to now and there could be this voice, this portal, this wormhole that opens up into the land of the other side of YouTube listeners, possibly hundreds of years into the future when someone's going to be listening to this because I'm not going to delete it. sort of waiting for this window into the future to open into the wall, but it's not going to happen. It hasn't happened yet. So, okay, this is your last chance, future listener, to listen. Okay, let's move on. Okay, channels. So I want to start on channels a little bit because channel coding. So this is now really the second half of the course. We're no longer talking about compression. We're talking about communication. So in compression, let's just remind ourselves what we're doing. We have some source distribution P of x, and it has an entropy H of x. And the goal is to compress that source, which is governed by that distribution, down to as few bits as possible. And we saw that the entropy was the fundamental limit of compression. And in some sense, when you compress something, if you compress it ideally, the compressed representation has a capacity. Let's say you've compressed something down into a thing of length n bits. And the capacity of something represented in n bits is sort of, in some sense, the entropy of n equal to n, because it basically says that any source whose entropy is equal to n, when you have n bits, can be compressed. That's the most you can store in those n bits. When you compress something down to n bits, you're fully utilizing the capacity because the original source is the entropy, and the entropy has been compressed down into those n bits. So in compressed form, the compressed bit string is in some sense at capacity. When you've uncompressed something, it's not really at capacity because in the uncompressed representation, you haven't fully utilized the capacity of that representation. So the notion of capacity actually makes sense in the case of compression. But in the compression case, you're talking about the capacity of a representation. We're going to be talking about capacity in a very different way in terms of channels. So with n bits, you can represent no more than n bits of information, obviously. So this is sort of what I just said. Compression can be seen as a process whereby we want to fully utilize the capacity of the compressed representation. In other words, anything that's compressed into n bits should ideally be something that has an entropy of n. Otherwise, if it has an entropy greater than n, we're not compressing efficiently. And remember the notion of efficiency. The efficiency is equal to the entropy divided by the expected length. And if the entropy is smaller than the expected length, then we're not getting good efficiency of the compression. Now we're going to talk about capacity in a different light. So now what we do is we have, and this is really a dual problem. I mean, it's a mathematical dual of compression. Communication and compression are the duals of each other, and as we will see in a very real sense. So now what we want to do is we want to transmit something over a channel. Okay, so before we do that, let's go back to Claude Shannon. Okay, Claude Shannon was, as you know, the inventor of information theory, and he's sort of the hero of the course. And so let's ask him what he says about communication. And if we were to ask him, if we were to time travel back to the 1940s and ask Claude Shannon, he'd say the following. He'd say, the fundamental problem of communication is that of reproducing at one point either exactly or approximately a message selected at another point. He would also say, which is something that we've acknowledged at the very beginning of this course, he would say frequently the messages have meaning, which is irrelevant to the engineering problem. Like, the meaning doesn't matter. We're just interested in an engineering problem. And remember what Claude Shannon looks like? There he is. He's speaking. So maybe what I should do is have like a big sort of cloud bubble here. There he is. It's Shannon talking there. So the question is there a limit to the rate of communication over a channel? And that's what we want to study. And we're going to see that the answer is yes, but more importantly, the channels that we're going to be dealing with are noisy. And we're going to see is that we can essentially achieve perfect or error-free communication over a channel even when it's noisy, and the rate's not going to be so bad, or the rate's not going to be crazy. So in other words, we can achieve perfect communication at a non-zero rate. Okay, so let's, again, we've been talking a lot about time travel. Let's pretend like we're in the 1930s. So everybody with me? Everybody pull out your history books. This is 1935. Okay, so what's going on? Here's some pictures of 1935. Stock market crashed. Well, actually, this is recently. We're in the Great Depression. We're in a worldwide economic depression, much more much worse than what we're in right now. The Great Depression. There's terrible industrial strife and terrible conditions in textile and mining industries. These are critical industries right now for worldwide economic health. There's crop prices are failing. We've had the Dust Bowl, at least in the United States, but there are, basically there's worldwide food shortages and soil depletions and farm mechanization problems. And things are really, really bad. Fascism is rising in the Nazi state. Japan, fascism is rising in Japan and in Italy. And the whole world is a big mess, right? It's really, really awful. Bad time. Radio, on the other hand, people are starting to use radio. Radio is getting big. People are broadcasting radio. This is before television. Everybody's talking to each other, primarily over AM radio. But basically, it's completely broadcast in an unsecure fashion. You basically broadcast this thing, anybody can listen. Point-to-point communications. If you're trying, this whole idea of secure communications that we're worried about now with the internet and everything, that just didn't even exist. I mean, people, if they were talking to each other, anybody could listen. And radio communications were fast, but they were completely insecure and they were not encrypted. Or if they were encrypted, the encryption mechanisms were really, really bad. And moreover, there was lots of noise. So radio encryption, radio transmissions was incredibly noisy. Especially, when bombs are going off and everything, radio encryption was not very, very, very efficient. Now there was Morse code. Morse code was around, but that's very, very slow. Even those people who are really good at these sort of two-pull Morse code machines, that was very, very slow. So what do? We want to fix this situation. We're in the 1930s, and we know that essentially communication happens in this analog way. We're at position A, another person is at position B, and we want to send an information over this noisy channel. And we're essentially assured that no matter what we send, there's going to be noise and distortion in the signals. Right? That's a guarantee. And here comes this guy, Shannon, who's saying, wait a second. Is it possible we can achieve perfect communication, error-free communication, at a high rate over this very, very imperfect communication mechanism, especially in this thing? I mean, communication is critical right now. It's critical for world health, because of how bad things are. It was really, really a crisis. Communication was a crisis. And right now, we take communication for granted. We've got cell phones, we've got the internet and everything. Even given all of these revelations that have recently surfaced, basically, communication is still, we're in a completely different state right now of communication. And the other question that Shannon was thinking about is there sort of some underlying upper bound on the information capable of being sent under different noise conditions? So he started thinking about these kinds of problems. And then, most critically, if we increase the transmission rate, if we have some sort of mechanism for measuring information of a source, if we increase the rate of information sent over this noisy channel, will the error rate necessarily increase? Without actually going to unbounded power. Like obviously you can send a signal with higher power. Whenever you go to a disco and everybody's talking and dancing and everything, one of the reasons why it's so loud, does anyone ever go dancing? No. You guys don't like tech gadgets? Well, has anyone ever been in a loud dance place? Raise your hand. No one? So no one has ever been? A few people have never been. Okay. So I've never been. I don't know what I'm talking about because I've never been there. But anyway, it's really loud, and the reason why it's loud is because the signal-noise ratio, you want it to be high. But the reason why the signal is loud, is high power, is because the noise is high. So you can actually communicate, which is sort of get a sense of the music by essentially making it loud, and we don't want to do that. We don't want to, it takes a lot of energy, and it also damages the receiver. So the question is, if we increase the transmission rate over a noisy channel, will the error rate increase? So raise your hand if you think yes. Raise your hand if you think no. Raise your hand if you think I don't know. Raise your hand if you think not necessarily. Okay, so the not necessarilies are are right. It depends. So it's not necessarily. And essentially what this means, and this is going to be the last slide of today, perhaps if that was true, if this sentence was true, then maybe the only way to achieve error-free communication is to have a rate of 0, which means we're not communicating at all, but certainly if we're not communicating at all, then at least we'll have a probability of error. So let's now think about a profile where we have the rate of communication, and we can think of it in terms of a generic rate, like how much information are we sending, or you could use our current definition of rate, which is number of bits per something, number of bits per use of something, like maybe number of bits per use of a channel. But let's just say it's some amount of information that we're sending over time, like a number of bits per second, whatever, some notion of rate. And if it's and this is the probability of error, the vertical axis. And what this profile would say is that the only way to get a probability of error is equal to 0 would be to have a 0 rate. Now, analog channels are kind of like that because no matter what you send over this analog channel that we saw before, it's going to be corrupted by noise. So we do know that, well, how do we get something that's not corrupted by noise? Don't send anything. So this was the prevailing wisdom by many at the time. And Shannon, in some sense, I think single-handedly, but certainly he talked to a lot of people, but I think he was the one who sort of single-handedly thought through this and realized that this was not the case. Okay, I have to end now. But I hope that this was an interesting and fun introduction to channel capacity. And if there are any questions, are there any questions about this? So in other words, what Shannon proved or showed or demonstrated to the world was that this need not be the situation. Okay, let's pause and start again soon.